Hello and welcome back. In the previous class, we have explained the concept of gradient descent. By now, hopefully you have a general picture of how gradient descent is and how to use gradient descent to minimize loss as well. In order to give you better insight in this lecture, we are going to formulate the mathematical model of training process. Now let's get started. For intuitive understanding, we take a very simple example. Suppose we have 10 digits from 0 to 9 and we want to classify them into 10 classes. Each image is 28 by 28 pixels. And this can be done by using a network of 10 neurons with 784 inputs for recognize image one by one. The first neuron is activated when we apply the digit 0. In a similar way, the last neuron is for the digit 9. So that means if we apply this one, the output will be 1, 0, 0, 0. And if we apply the digit 9 to the network, the output will be with 0, 0, 0, and 1, respectively. We conduct the mathematical model by step-by-step formulate the equation for each process. First, we calculate the output for each neuron. In this, we calculate the output for the neuron J, the output neuron J. And in this, we obtain the Aj equal to the summation of the inputs multiplied by the synaptic way. And keep in mind that in this, we denote Wj I equal to the synaptic way for the inputs I connect to the neuron J. That is the we use this notation for all of this in this class, and then we pass the value to the sigma function. This we use the activation function with sigma function. Then we calculate the loss function. The loss function is the error of all outputs. We have the 10 outputs, and we calculate for all sample. So we have 10 digits. So we have 10 samples. And in this equation, we use this subscript for the output index, and we use this one for the sample. We have 10 samples, so this is T from 1 to 10, and this is we have 10 outputs, so we have J is from 1 to 10 too. And in order to make it more simpler, we simplify this one for only one output neuron, and one output neuron we have also calculate the error for all sample. In this case, we have 10 sample. And in this, keep in mind that we have already calculated in reverse step J and O. We use the O to represent the predictive output. And we apply the concept of gradient descent. Gradient descent means we minimize loss function by update or by change synaptic way or change parameter. And how can we change parameter? We already discussed on the previous class. We go in the opposite direction of the gradient, and this is gradient descent. So we update by minus gradient descent time learning rate or the percentage of the update. And this is the concept of gradient descent we have already explained in the previous. And in this the loss function is something equal to something square in this, and this is the value, and this is the function. This can be the function of a trait, and a trait is a function of w and x. So that we can say that n loss function is a function of w and x, and we keep this one. We want to adjust this one. So in this case, we consider w as a variable. In order to calculate the derivative of loss function with respect to w trait y, that means we have this one, the output this one, and w, this one, w trait y. We want to update this one. So when we use the power rule, and the chain rule for calculate the derivative. For the power rule, we have that the derivative of loss function with respect to w trait I equal to 2 times of this one. We keep the same this one, and we get the derivative of output relative to w trait y. And from here, we use the chain rule again. We can obtain that this one, derivative of output relative to a time derivative of a relative to w trait y at w trait I. For calculating the derivative of this one, we can use the, because OT is the sigma function with the input the a trait. So by calculating, we can obtain the derivative of this derivative of O trait t relative to a trait t equal to OT 1 minus O trait t. That's the equation. We can do some calculate, and we obtain this one. So finally, we can substitute this one into this one, and we obtain the derivative of loss function relative to w trait I equal to minus 2 divided by 10. The 10 represents the average, and we calculate for 10 sample, and we can have this equation. And don't forget to multiply x trait, because we have x trait, because the derivative of a trait, this is the derivative of a trait t relative to w trait e equal to, because in this equation to x I, so this x I trait, and we have this one. So we use this, we update the w update by plus the delta w trait I, and in here w trait I equal to this one, because it is this is minus and this is minus, so we have a plus, this is plus, and we don't see the minus in here, and we multiply by the learning rate. This is learning rate, and this is learning rate, and this is, we use this equation for update parameter. So far we have figured out, and we have formulated a set of equations for the training process using the gradient descent, and hopefully this makes you understand how gradient descent can be applied to a simple network for a specific or for particular application in this video. And next we will try to deploy this concept by using a matrix. Using a matrix and matrix multiplication in Python can easily deploy this, implement the concept of gradient descent for a simple a simple example we already discussed so far. Okay, and see you next lecture.